This project uses the NodeMCU ESP8266 microcontroller paired with the Arduino IDE. Since the ESP is not a default board, it does not show up in the board's manager used to add new MCUs to the IDE. To add the ESP, we first need to enter this JSON string, which adds all the ESP MCU libraries, including the one we need, to the board's manager. Once that is done, the ESP8266 library is now available to install to the IDE. We will also require these libraries responsible for making the ESP communicate with the web server and the Blynk app. Now that the board is installed, we can configure the board for the IDE. We will be using the NodeMCU 1.0 board for this configuration. The ESP has two built-in LEDs corresponding to GPIO pins 2 and 16. The default upload and baud rate for the ESP is set at 115 kHz using the COM7 UART bridge port between the ESP and the computer. The IDE is now successfully configured. The circuit shown here comprises a simple hardware implementation where the two on-board LEDs and the two external LEDs represent outputs to various devices and applications that could be used in an actual future project implementation.
I'll be explaining our Blynk server implementation. The most commonly used one, hosted by Blynk themselves, is a great way to test out small sample programs. However, the cap on available features and the risk of sharing a server with thousands of people around the world limits its use. Any Blynk server must perform a variety of tasks simultaneously. It must store a secure database with user information, auth tokens for each project, and all the data about the projects, such as the type and number of widgets and the settings for each one. It must also be able to communicate with both the Blynk app instances on users' phones, as well as the controlled board, like the NodeMCU in this case, for real-time updation of data. At the same time, it should have inbuilt limitations set, such as the maximum number of requests per user, number of boards controlled, etc. In the default Blynk server, these are set extremely low due to the sheer number of users it supports. One may ask, why implement your own server on the cloud? A regular custom server runs only on the local network, which means you'll have to be connected to the same Wi-Fi network or via LAN to the same router. This goes against one of the main purposes of IIoT, which is to make use of the internet to remotely control devices. Due to the shortage of public IPv4 addresses, most ISPs use network access translation to support more users with a limited number of these public IPs. This, however, makes it impossible to host a server from a device at one's home itself. A public cloud server like the default Blynk server comes with its own usage and data security limitations as mentioned before. Hosting one's own custom server on the cloud does away with both these sets of issues. One can remotely access their devices while at the same time being assured that the data stored is yours only, and that too in a more secure manner. It also allows for easy scaling up of any solutions built on the platform. Our Blynk server setup is hosted on Google Cloud. It runs on a compute engine virtual machine running Ubuntu and has a static IP address linked to it for ease of use. This also allows us to use a dynamic domain name service to host it with its own URL. The ports required for HTTP, HTTPS, MQTT, and SMTP are all open so that the server can send the auth token emails from the linked email ID and can communicate with the clients and devices anywhere in the world via the internet. This server also runs almost 24/7 with minimal downtime. For the project development itself, there are just three extra steps for using the custom server as shown here. Users must make a separate account on the custom server itself before being able to use it, and this data is not stored publicly. The URL and port 9443 are used by the app, and the IP address, which is the same as the one linked to the URL, and port 80 are used by the NodeMCU. The server will be kept live until the end of June and will be periodically checked for proper functioning. These three steps can be used to check the working of the server by creating a new account and project on it. The server also features its own portal, which allows the administrator to conveniently monitor the server, users, connected devices, etc. from anywhere in the world. It can also be used to enable or disable the creation of new users, deleting added users, changing the limitations of new projects hosted, etc. The login page for this can be accessed via the link or QR code given here until the server is live. The server uses a large variety of protocols interconnected with each other to perform all the functions seamlessly. Right from the physical layer to the application layer, here are the protocols used and the purposes of each one.
At the top of the code, we have defined several macros which we will be using for sending and receiving information about the microcontroller LED states. To begin, we will first have to define an async web server object on port 80 to allow us to control the onboard operations remotely. When we launch the web server, the page asks us for a username and password to confirm that we are authorized to use it. Once we log in, we can see checkboxes which control whether the particular LED is on or off, along with their respective labels. All of the checkboxes call the JavaScript function toggle checkbox, which accepts the calling element as a parameter. This can be seen in the onClick attribute of the checkbox inputs. The function retrieves the ID of the calling element and sends a request to the /update URL. Outside the web page content, we can see that when the ESP receives a request on the /update URL, it first checks which parameter is present in the request. Once that is done, it retrieves the state to which the LED needs to be changed and changes it using a digital write on the required pin. Going back to the web page code, we also have a set interval method which we have defined to make sure that the web page is updated every second with the correct state of all the LEDs. For example, if someone were to control the components from the Blynk app or perhaps an attached button, the LED states would update according to the changes made. To accomplish this, the method creates and sends a request to the fetch state URL, which reads and returns the current states of all the LEDs as a comma separated string. Once the method receives the information, it updates the states on the web page as required. The last portion of the web page contains a slider which can be used to change the brightness of the green LED. On changing the slider position, the JavaScript function update value is called. This function retrieves the value of the slider and updates the label with this value. The /update URL handler mentioned previously also handles the changes made to the slider on the hardware side. The brightness is changed using an analog write on the required pin. The slider label initially contains a placeholder variable called brightness value. The processor function replaces this placeholder variable with the actual value of the brightness of the green LED when the web page is first created. Finally, we have the logout button, which sends a request to the /logout URL. After 1 second of this, it navigates to the logged out page. The HTML code of this page contains a link that will allow us to go back to the root URL where we first started, along with a message mentioning that the page and all browser tabs will have to be closed to complete the logout process. This program also has action-based notifications that are sent to the phone using the Blynk app. This allows for additional security measures to be put in place, like an email notification being sent when someone tries to log into the web server, or a push notification being sent to the phone when the red LED is turned on through the web server.